Hello guys, I'm Eshan Tripathi, Physics faculty at askIITians, and welcome to the last lecture of Work Energy of Power of Grade 9th. So we have learned a lot of things in work till now, work, whenever energy theorem, and then we have conservation of energy, and pretty much interesting topics we have learned, including all the topics of mechanics we have learned till grade 9, and very interesting questions as you must have practiced, can be formed from this, including all the topics earlier. So that made this topic pretty interesting. So in this last lecture, as I mentioned the previous lecture also, we are going to discuss continuity equation and Bernoulli's theorem. Now this is like usage of the concepts of work energy to understand one of the topics that we have learned, which is fluids. So we discussed about pressure in fluids in the chapter gravitation. So in this chapter, as I'm going to, let me just share the screen. Yeah. So as in this lecture, I told you we are going to discuss these two topics, equation of continuity and Bernoulli's principle. So Bernoulli's principle has really good applications in real life. And that is why you can see an image over here where there's a car, and particularly I talk about racing cars. And they use this concept of Bernoulli, not just racing cars, but airplanes fly on the basis of Bernoulli's theorem. The swing that people give to a cricket ball, that's on the basis of Bernoulli's theorem. So many interesting things, aerodynamics, whole of the aerodynamics works on Bernoulli's theorem, Bernoulli's principle, but we'll see what it is. So for now, let's begin with the simpler topic, the introductory topic for that, which is equation of continuity. Now, equation of continuity as written is A1 V1 equal A2 V2. But before that, what are we even talking about? See, imagine there is a pipe which is of this shape, as we have shown over here. The pipe is thicker on the left and it becomes thinner as one moves on the right. So what do you think? What does your intuition say? At which point will the speed of liquid be more? Will it travel faster at point 1? Like, will V1 be more? Or will it travel faster at point 2? Or V2 will be more? What do you think? What's your intuition? So imagine, if a pipe becomes thinner, is it that liquid will travel faster or will it travel slower? One of the simplest examples you can take of it is like when you're trying to water plants or using a pipe. So you are holding that pipe, let me draw over here. You are standing over here, holding the pipe of water. Okay. Now water is coming out of it. Fine, water is falling. Now, if you want to increase the range of this falling water, basically, if you want to increase the speed with which the water is coming out, what will you do? Don't you think you cover half of the pipe or a little bit more or maybe a little bit less fraction of a pipe with your finger? When you cover that fraction, suddenly the rest of the liquid, like the rest of the area through which liquid is coming out, the speed of it increases. And that goes farther, right? You cover it fractional, like partially by your finger, and it starts to travel with faster speed. That means V2 is going to be greater than V1 in this particular case. If area is reduced, speed is going to increase. What's the reason? To understand the reason, guys, imagine it like this. Do not imagine it to be water, but imagine there's a highway which is getting thinner as one moves towards right. The highway becomes thinner. Now cars are traveling on this highway. Okay, you are a driver, one of the drivers of this driving on this highway. So 4 cars were moving on this highway, and let's say all of them are going to move together. Now imagine, as soon as a tunnel comes, which is a bit thinner, what decision should the drivers make so that they do not collide with each other? Can you imagine? As soon as they are going to get closer to this tunnel, they will decide that now they're going to speed up the car. So that as soon as the next car comes in, they have already passed through the tunnel because only 1 or 2 cars are allowed in this. So this time they'll travel faster so that in the same time, more cars can be accommodated inside that tunnel. The same number of cars can come in and then go out also. So this, what is happening with the cars over here is the same thing which is happening with water over here. In the case of cars, that like if in 1 second, 4 cars are traveling through this part, in the same 1 second, 4 cars should travel through the thinner tunnel also. Otherwise, they'll collide. Whatever number of cars are coming, same number of cars should go on the other side also. Otherwise, they'll collide. Similarly, we are saying whatever amount of water will be coming in to this cross section, in the same time, same amount of water should be going out of the other side. So that is why we are saying as A increases, B decreases, as A decreases, B increases. They are inversely proportional. Now, what exactly is A1, V1, A2, V2? What is the physical meaning of A multiplied by V? Let's try to see this. Guys, let us say in time dt, in a small time dt, like dt means a very, very small amount of time. If the liquid is flowing, let me take a cross section through which the liquid is flowing. Let us draw it over here. Yeah, this is the cross section through which liquid is flowing. In dt time, it's flowing with some speed. Let's say that the speed is v. So can I say in dt time, it would have traveled a bit of distance? Okay, I'm so sorry. Yeah, let us say they are traveling with speed v. And in dt amount of time, they would have traveled a bit towards right. But in dt time, how much distance would they have traveled? If they are traveling with speed v, small time dt, speed into small time dt is the small distance travel, right? So basically, what is the volume of liquid flown? What is the volume of liquid flown in dt time? Volume. That volume is going to be the cross-sectional area of this part. Let's call it A, multiplied by the width of it. That's A into dx. That is A into v dt. So small volume flown dv is AV dt. So guys, what is AV? Can I say that's rate of flow of volume? Rate of flow of volume, which is dv by dt. Guys, v is not velocity over here. This capital V I'm writing on the left. This is rate, this is volume. So small volume dv by small time dt is A into speed v, small a into velocity. So rate of flow of volume is what we called area into velocity. And this I represent by symbol Q. So guys, this Q, which we are writing as A1, V1 into A2, V2 is actually rate of flow of volume. What we are saying is, whatever amount of volume is flowing through this left cross section over here, same amount of volume is flowing through the right cross section in the same time. In fact, you can check the units also. What are the units of area? Area's unit is meter square. What is the unit of velocity? Meters per second. If I multiply them, meter square multiplied by meter per second, that will be meter cube per second. Yes, it is volume flowing per second. This much meter cube of water is flowing every second, per second. So this is what equation of continuity is. Whatever is the rate of flow of water through one cross section area, otherwise water cannot compress. Can you imagine it compressing? But yes, water is not compressing. So that is why we are using this. So I hope this is clear. The equation of continuity, very important equation you need to learn. Now, this is a concept that you purely learn in class 11th only, but from competitive point of view, we are studying this. So we are going to learn this A1 V1 equals to A2 V2. So let's see this. A liquid flows through a pipe of diameter 10 centimeter with a speed of 9 centimeters per second. If the diameter of pipe then decreases to 6 centimeter, what's the new velocity of the liquid? So pretty simple question, nothing much in this. Let's try this. Let's draw the pipe. It's becoming thinner because earlier diameter was 10 centimeter. Now it's only 6 centimeter. So the diameter on the left, I'm going to write as over here, the diameter is 10 centimeter. I like to write everything in SI units. So I can, if you want, you can write it as 0.1 meters, although it's not necessary here. And diameter over here, D2, that's given to be 6 centimeter, or you can write it as 0.06 meters, your choice. Now let's use the equation, the continuity equation, and let's see how it works out. A1V1 is equal to A2V2. Now area of a circular cross section is pi r square, but radius is not given, diameter is given. So can I say that's pi d1 square by 4, because radius I've written as d by 2 and it has been squared. So d1 square by 4 into v1 equals to pi d2 square by 4 into v2. And if you just reorient the equation, you'll get v2 equals to v1 times d1 square by d2 square. That's the velocity second. So you can say it's 9 multiplied by 6 centimeter per second. That is how much? 6165, 150 centimeters per second. Yeah. Mm. Sorry, divided by 36. That's what I was thinking. Yeah. Going to divide by 36. So it's going to be 25. Yeah, that's what. So it's 25 centimeters per second. Okay, fine. So very simple question. Liquid would just speed up from 9 centimeter speed to 25 centimeter per second. Okay, so with this, let's move to the next concept, which is Bernoulli's equation. Now, what it says is, imagine guys, what has been drawn over here, imagine that there is a pipe which is carrying liquid upwards. Okay, think about liquid was slow, V1, but as it moves up, the liquid gets faster, V2. Is that possible? Yeah, definitely. Motors can do this. You can use an electric motor to supply like the liquid to a higher height, and it should speed up also. Yeah, that's possible. But think about conservation of energy. What about the kinetic energy as we are moving up? It's increasing or decreasing? As I've said, liquid was being pumped in slower at the bottom, and it's getting faster at the top. So kinetic energy is increasing. Then think about this: the potential energy. I did check the gravitational potential energy. Is it increasing or decreasing? It is also increasing, right? Because height is increasing. But how is that possible? You must be thinking, how is that possible? Kinetic energy also increasing, gravitational potential energy also increasing. That doesn't seem to be possible according to conservation of energy. No. Loss in kinetic energy is gain in gravitational potential energy and vice versa if no other forces act. But imagine now, it is possible to like speed up the liquid and increase its height only if you are using a motor. Basically, you have a motor which is going to pressurize liquid over here at the source, and there will be comparatively lesser pressure at the top. Basically, the pressure at point 1 is going to be greater than pressure at point 2. And it's this pressure difference which is increasing the height also and speeding it up also. So basically, this is coming from work energy theorem. What it says is work done by pressure difference is equal to the gain in kinetic energy also plus gain in gravitational potential energy also. So basically, it's the work energy theorem that is working over here. And if you just use the work energy theorem and change its form a little bit, you don't need to know how that is done. We'll be learning it later on. But in class 9, that's all we need to know. That a little bit manipulation of this work energy theorem can actually give us this equation called Bernoulli's equation. It's the same thing as that. Okay. So the equation says pressure at any point plus half rho rho is density into velocity square to at that other point. That is what this equation says. see a simple. Let's just don't think a lot about it right now. Let's see a simple application of it first. Then we'll see some more complex things. So for example, if I say there is this container filled with liquid. Okay. There is a point B over here at the depth of H from the top. And we asked the pressure at point B. The density of the liquid is given to be rho. What's the pressure at point B? Now I know. I'll quickly say rho GH. Atmospheric pressure plus rho GH. Right? Pressure from the top, and further you have gone down by a depth H. That's fine. But we want to use, because we need to practice. We know how to get the answer to this. But we need to practice Bernoulli's equation also. So let's do that. And using that, let's obtain the answer. So for Bernoulli's equation, always 2 points are important. Point 1, point 2. Any 2 points you can take. But at least one of the points should be the one over which you are finding the pressure, right? So B point needs to be one of them. And the other point should be a point of which you know things. So one point is going to be the one of which we will find things. Another one should be of which we know things already. So a very interesting point over here of that is the point exposed to atmosphere. That is, speed at point A square plus rho g into height of point A is equal to pressure at point 2. It's too light. Is equal to pressure at point B plus half rho into speed at point B square plus rho g height at point B. Now see guys, any of these things that you already know? Yeah, the speed is 0. The liquid is not moving, it's at rest. So VA, VB, both terms will be 0. Any other thing we know? Yeah, point A. Point A is a point open to atmosphere. Point A is open to atmosphere. That means the pressure at point A is atmospheric pressure already. So we can say atmospheric pressure plus rho g HA is equal to pressure at B plus rho g HB. So that means pressure at point B is atmospheric pressure plus rho g HA minus HB. What is HA minus HB? HA minus HB is the height difference between them, which in the question is given to be H. So can I say pressure at point B is atmospheric pressure plus rho g H, because HA minus HB is H, and then we get the answer. So I hope this is clear how we use this equation to get an answer that we already knew from the previous theory. Okay. Let's see another question on this, including some terms of speed. Yeah, let's see. It's given that there is a pipe through which liquid is flowing at some rate. Diameter is 1 meters. Later on, the diameter halves. Basically, if I draw, the pipe is thicker on the left, but as one moves towards right, it gets thinner. I drew it to be too thin, but yeah. The diameter on the left is given to be 1 meters. Basically, this diameter, D1, is 1 meters. And the diameter on the right, D2, that is half a meter. Okay. What else is given? Let's see. The rate of flow of water is given. 2 meter cube per second. What can we know from this? Guys, we know the diameter. So we can find velocity at both the points now, because we know Q is equal to A1 V1 for the left cross section. And also we know Q is equal to A2 V2 for the cross section on the right. Now, what is the value of area? Area is pi d1 square by 4 into V1 equals to Q, and pi d2 square by 4 into V2 is equal to also Q. So from these relations, we can actually find out the speeds with which liquid is flowing at this point, and of course faster at this point. So from this, the value of V1 that I get is I get the value of V1 as 4q by pi V1 square. That is 4 times 2 time divided by pi into t square, that is 1 square. That's 8 by pi meters per second. That is the speed of liquid at that point. Okay. Similarly, we can find the speed V2 at this point. That will come out to be 4 times again q divided by pi. This time the diameter is 0.5 h square. That will be 4 times, so that's 32 by pi meters per second. So it's 4 times the speed on the left because area is 1 by 4. Radius is half, so the diameter is half, radius is half, area is 1/4. So speed is 4 times, it had to be so. Okay, so I know the velocity at first point and the second point, and then I have been given the pressure at point 1 also. In the question, it says that pressure at this point is 8 kilopascals. P1 is given to be 8 kilopascals. Okay, that's 8,000 pascals. We have been asked the pressure at point 2. So let's use Bernoulli's equation. Using Bernoulli's equation, P1 plus half rho V1 square plus rho G, height of point 1, is equal to P2 plus half rho V2 square plus rho G into height of 2. Now, what all things do we know? One very important fact that we know is their heights are same now. What if, because the point 1 and the point 2 are at the same heights. There's no height difference. So H1 is equal to H2 and this term gets cancelled from both sides. These are equal. I'm not saying they are 0, but they are cancelling because they're equal. H1 is equal to H2. Basically, H1 minus H2, if you get, that will be 0. So now it's simple. P2 equals to P1 plus half rho V1 square minus V2 square. And that's it. Nothing left in this. Just put in the values. So pressure at this is 1000 plus half into water is flowing. We know density of water is 1000 kg per meter cube SI units into V1 square minus V2 square. That's 8 by pi square minus 32 by pi square. So you come out to be a little bit negative value. So pressure is going to be whatever pascals you get from this, that will be the answer. This many pascals. Okay, this many pascals. So yeah, it's going to be a little bit less than at 8,000, 80K. Okay, that was 80K. I'm so sorry. It was 80K. Yeah, so nothing, no issues in this. Become 80,000 pascals. Okay, so that's how we can do this. The pressure at the end at point 2 is going to be a little bit less than 80K pascals. Okay, so on the basis of this Bernoulli's principle, as I said, there are many interesting phenomena that can be understood. And one of them is velocity of efflux. Very interesting one. As I have shown over here, guys, imagine if there's a container filled with liquid and we make a small hole inside it. The water will start coming out now, and it won't just come out slowly. It will come out with a speed. So the velocity with which this liquid comes out, that is what we call velocity of efflux. When you make a small hole, how the liquid is going to come out of it. That's the speed. That speed is called velocity of efflux. By using the Bernoulli's theorem, we can actually find out the velocity of efflux. Let's see, this is really, really interesting. There's a container filled with liquid, let's say to some particular height. A small hole, let's say very small hole has been made. So I'm marking this over here. Very small hole has been made at the bottom. So what will happen when the hole is made? Perpendicularly, the liquid is going to come out like a jet of water is going to come out with some speed. That speed we need to. Hole is very small. That's what we're imagining. Let's say that the density of the liquid is rho, and the depth at which this hole has been made from the top, that's h. We are supposed to find the speed v with which it comes out. So again, since we're using Bernoulli, we need 2 points over which we need to consider the equation. So what will the 2 points be? What are the 2 points of which you know everything or you need to find things off? So first point will be the point at which you're finding speed. So can I say one point is going to be the liquid which has come out of the container? Basically this liquid, this point. The point one which is present outside, because we are asking what is the speed of liquid when it comes out of the container. Some people might be thinking, oh, we can take this point also. It is at same height. It is at same height, but that liquid is not moving. That is inside the container. The liquid starts moving when it comes out. So the question is, what is the speed at point one? And that is why we're taking it outside. And what is the other point of which you know things? That is the point at the top. You know its atmospheric pressure and all. Okay. So let's start with this. Let's use Bernoulli. P1 plus half rho V1 square plus rho G H1 is equal to P2 plus half rho V2 square plus rho G H2. That's the Bernoulli equation. Do we know pressure at any point? Think about it. Yeah, we do. Pressure at point 2 is definitely atmospheric pressure. It's open to atmosphere, right? 2 point is at the top, open to atmosphere. It's atmospheric pressure. The question is, do you know the pressure at point 1? What is the pressure at point 1? Think about this. Little bit more than atmospheric pressure or less than atmospheric pressure or equal to atmospheric pressure? If you're thinking the pressure is more than atmospheric pressure because it's a bit deeper, then guys, you are actually thinking about point V over here, which is inside the liquid. You are thinking pressure will be more P atmosphere plus rho GH because of the liquid present above it. No, you're talking about the point which is present inside the container. Think, when it has actually come out over here, then what is the pressure? When it has come out to the atmosphere. It has been exposed to the atmosphere, and pressure at point 1 is atmospheric pressure only. Getting this? So P1 is equal to P2 equals to atmospheric pressure, and hence they both cancel. Interesting. Anything else we know of? V1 though is the quantity that we need to find. Let's write it over here. Half rho V1 is what we are calling V is equal to rho G H2 minus H1, bringing that on the right side, plus half rho V2 square. Guys, do we know anything about value of V2? What is the speed of the liquid at point 2? Will the liquid at point 2 be moving up or down, or will it stay over there? Technically, it will be moving down because as liquid is coming out, the level of liquid will fall. You can see in this picture also. As the liquid come out, the level of liquid will fall. But we are saying there's a very small hole. So can you imagine if the hole is very, very small, hardly liquid is coming out. Like liquid is coming out at a rate, but very small amount of liquid is coming out. So that won't affect the rate or like the height of the container a lot. In fact, the liquid will be coming down, but very, 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 very slowly. V2 will be tending to 0. That's the approximation we are using. And we will say half rho V square equals to rho G H2 minus H1, the height difference between point 2 and point 1. That is given to the H. So interestingly, rho cancels rho and V becomes root 2gh, like the speed in free fall. This is the interesting part. The water comes out as if with a speed as if it has fallen from this height edge. So it's a matter of coincidence that it's coming out like that. You can call it conservation of energy because Bernoulli has been derived from conservation of energy. But yeah, the answer comes out to be the same. So if there's a small hole at a depth h, you can imagine the deeper the hole is made, more the value of h, more is going to be the value of v, isn't it? You make a hole at the top, water is going to come out slower, but the deeper hole you make, more pressure difference, faster it's going to come out. So that's what velocity of efflux is. And let's do just one question It might seem very long, but it's very small question actually. Just read it and try this question. Suppose that a huge tank, 50-meter high, filled with water, is open to atmosphere. So till 50 meters height, it is filled with water. Now, bullet is hit on the on this container, and the hole is pierced at a height of 2 meters above the ground. Like basically, a hole has been made over here by a bullet at 2 meters height. The hole is very small compared to size of tank. Again, very small hole approximately. Basically, you have to find the velocity of reflux. And since we have already derived it, we can say V equals to root 2GH. But the question is, what's the value of H that we are taking? H is the depth at which the hole is made. So that depth you can see is 48 meters actually, 50 minus 2. That's root 2 times 10 times 48. Okay, so this much meters per second is going to be the speed with which the liquid comes out of this. Okay, you can just write it in decimals, that's also okay. So this is how we do this. Just one equation got root 2GH, easy to remember also. And that's it about this whole chapter, work energy theorem. I hope you guys enjoyed this. And I would say if you have any doubts related to anything, you can always post on the maths discussion forum. The questions can be answered there. And okay, all the best. Okay, bye-bye. The liquid starts moving when it comes out. So the question is, what is this speed at point 1? And that is why we're taking it outside. And what is the other point of which you know things? That is the point at the top. You know its atmospheric pressure and all. Okay. So let's start with this. Let's use Bernoulli. P1 plus half rho V1 square plus rho GH1 is equal to P2 plus half rho V2 square plus rho GH2. That's the Bernoulli equation. Do we know pressure at any point? Think about it. Yeah, we do. Pressure at point 2 is definitely atmospheric pressure. It's open to atmosphere, right? 2 point is at the top, open to atmosphere. It's atmospheric pressure. The question is, do you know the pressure at point 1? What is the pressure at point 1? Think about this. Little bit more than atmospheric pressure or less than atmospheric pressure or equal to atmospheric pressure? If you're thinking the pressure is more than atmospheric pressure because it's a bit deeper, then guys, you are actually thinking about point 3 over here, which is inside the liquid. You are thinking pressure will be more P atmosphere plus rho GH because of the liquid present above it. No, you're talking about the point which is present inside the container. Think, when it has actually come out over here, then what is the pressure? When it has come out to the atmosphere. It has been exposed to the atmosphere, and pressure at point 1 is atmospheric pressure only. Getting this? So P1 is equal to P2 equals to atmospheric pressure, and hence they both cancel. Interesting. Anything else we know of? V1 though is the quantity that we need to find. Let's write it over here. Half rho V1 is what we are calling V is equal to rho G H2 minus H1, bringing that on the right side, plus half rho V2 square. Guys, do we know anything about value of V2? What is the speed of the liquid at point 2? Will the liquid at point 2 be moving up or down, or will it stay over there? Technically, it will be moving down because as liquid is coming out, the level of liquid will fall. You can see in this picture also. As the liquid come out, the level of liquid will fall. But we are saying there's a very small hole. So can you imagine if the hole is very, very small, hardly liquid is coming out. Like liquid is coming out at a rate, but very small amount of liquid is coming out. So that won't affect the rate or like the height of the container a lot. In fact, the liquid will be coming down, but very slowly. V2 will be tending to 0. That's the approximation we are using. And we will say half rho V square equals to rho G H2 minus H1, the height difference between 0.2 and 0.1. That is given to be H. So interestingly, rho cancels rho and V becomes root 2gh, like the speed in free fall. This is the interesting part. The water comes out as if with a speed as if it has fallen from this height h. So it's a matter of coincidence that's coming out like that. You can call it conservation of energy because Bernoulli has been derived from conservation of energy. But yeah, the answer comes out to be the same. So if there's a small hole at a depth h, you can imagine the deeper the hole is made, more the value of h, more is going to be the value of v, isn't it? You make a hole at the top, water is going to come out slower. But the deeper hole you make, more pressure difference, faster it's going to come out. That's what velocity of efflux is. And let's do just one question. It might seem very long, but it's very small question actually. Just read it and try this question. Suppose that a huge tank, 50-meter high, filled with water, is open to atmosphere. So till 50 meters height, it is filled with water. Now, bullet is hit on the this container, and the hole is pierced at a height of 2 meters above the ground. Like basically, a hole has been made over here by a bullet at 2 meters height. The hole is very small compared to size of tank. Again, very small hole approximately. Basically, you have to find the velocity of reflux. And since we have already derived it, we can say V equals to root 2gh. But the question is, what's the value of h that we are taking? H is the depth at which the hole is made. So that depth you can see is 48 meters actually, 50 minus 2. That's root 2 times 10 times 48. Okay, so this much meters per second is going to be the speed with which the liquid comes out of this. Okay, you can just write it in decimals, that's also okay. So this is how we do this. Just one equation got root 2gh, easy to remember also. And that's it about this whole chapter, work energy theorem. I hope you guys enjoyed this. And I would say if you have any doubts related to anything, you can always post on the mass discussion forum. The questions can be answered there. And okay, all the best. Okay, bye-bye.